Okay, today we are going over lesson 13 on derivatives of inverse functions and also derivatives of natural log and logarithmic functions. First off, today we're going to start with how to find the derivative of an inverse function. And the simplest way to explain inverse is the formula to find the derivative of inverse is a reciprocal. So the actual formula, derivative of an inverse, is 1 over derivative of your actual function. So let's look at one example. We have f of x equal to x to the fourth minus 5x minus 2,366. And we're also given x is equal to 0, which is f of 7. And we need to find the derivative of our inverse function with respect to x. The first step is to take the first derivative of your given function. So that would be just 4x cubed minus 5. Now here's where the inverse part comes in. Using this simple formula to find the derivative of the inverse, we're just simply taking 1 over our given derivative, or the derivative we just found. So this would be now, following the formula, 1 over 4x cubed minus 5. Now we need to find f of 7. So quite simply, where you see an x in your derivative inverse, you plug in 7. So we have 1 over 4 times 7 cubed minus 5. And following order of operations, when we do 7 cubed, that gives us 343 times 4, and then minus 5. So just like that, our final answer is 1 over 1,367. That's how you find the value of inverse's derivative. Let's look at a similar problem. Given f of x equal to x cubed plus 7x squared minus 91, we need to find the derivative of our inverse when x is equal to 0 or f of negative 2. First step again, before we use the inverse derivative formula, take the first derivative of your function. So f prime of x is equal to 3x squared plus 14x. Now, to make it an inverse, just follow the formula up here, and we'll make it 1 over our derivative. So that is the derivative of our inverse function, 1 over 3x squared plus 14x, I'm sorry. Now, to find the value f of negative 2, you just replace each x in your derivative inverse with negative 2. So we have now 1 over 3 times negative 2 squared plus 14 times negative 2. And when we do all of the calculations, our final value of our derivative's inverse is 1 over negative 16. So that's all you have to do when you're asked to find the derivative of an inverse function, and you just take it one step further if you have to find the value of a derivative inverse. The other thing, the other major thing we need to discuss from lesson 13 is derivatives of natural logs and logarithmic functions. But before we work out some problems, let me go over the various derivative rules with you. Starting with the derivative of natural log of u is equal to 1 over u times the derivative of u. If you have base a raised to some u power, to take the first derivative of it would be the formula a to the u power still times natural log of a. And then using chain rule, you will take the derivative of your exponent u. With exponential functions, if you had to take the derivative of e to the u power, derivative of e to the u is still e to the u times the derivative of your exponent u. And last but not least, to take the derivative of a log function, where you have log base a of some function u, to take the derivative of a log function in this form, it would be a fraction, 1 over whatever u is, times natural log of a, where a is your base, times the derivative of your function u. So these are all the derivative rules you need to know for logs, natural logs, and also exponential functions. You will also need to use some of the basic algebraic rules for logs and natural logs. Let's start with this example. We have y equal to the natural log, and we have a fraction in parentheses, x squared plus 4 to the 5th power, all over the square root of 5 minus x. And we need to find the derivative of y with respect to x. In other words, we're trying to find the ratio dy over dx. Now, before we take the derivative, let's use the quotient rule and also the exponent law for natural logs. Quotient rule, if you remember, if you have a fraction, then you can split this natural log into two separate natural logs as a difference. So we have natural log of x squared plus 4 to the 5th power minus natural log, and I'm going to rewrite that radical where it also contains an exponent. That would be 5 minus x to the 1/2 power. There's one other law we can use before we take the derivative, and that is the exponent law. The exponent law for natural logs, you take each original exponent and move it to the front. So that would be 5 natural log of x squared plus 4 minus 1/2 natural log of 5 minus x. Now we're ready to take the first derivative. Now recall from lesson 12, I believe, implicit differentiation. The derivative of y is just 1, but because we're taking the derivative of y with respect to x, then we have a dy dx over here. Now to take the natural log, the derivative of a natural log of any function besides x, we immediately put 1 over our given function. And I'm just going to put this 5 in the numerator. And then the rest of the natural log derivative rule here is you take the derivative of your function, or derivative of x squared plus 4, minus 1/2, and the derivative of natural log of 5 minus x is 1 over 5 minus x times the derivative of 5 minus x. Going back to the first part, the derivative of x squared plus 4 is 2x. And the derivative of 5 minus x is negative 1. So let's put everything together up here and get our final first derivative. So dy over dx equal to, multiply the 5 and the 2x together to give you 10x, all over x squared plus 4. The negative 1 times negative 1/2 changes to a positive 1/2 times the 5 minus x. And as far as I'm concerned, you can leave your answer as two fractions. Let's look at a similar problem where you're just asked to find dy over some other independent variable. It could be with respect to x, it could be with respect to time, or it could be like in the next problem with respect to the Greek letter theta. So here's our question. Find the derivative of y with respect to theta, or dy d theta is what we're looking for. If we have y equal to natural log and we have a fraction, e to the 8 theta power all over 1 plus e to the 8 theta power. Before we take the first derivative, use the quotient rule again to break down your natural log fraction. So we have natural log e to the 8 theta minus natural log 1 plus e to the 8 theta Now, for the first natural log, we can use the exponent law and move the 8 theta to the front. And bring down the rest of our problem. Now, we know from algebra that the natural log of e is 1. So really what we have there in the first part is just 8 theta. Now we're ready to take the first derivative. The derivative of y with respect to theta is just dy d theta. The derivative of 8 theta is the same as taking the derivative of 8x. That's just plain 8. And to take the derivative of the second natural log, you automatically put 1 over your given function. And then using the chain rule, take the derivative of your function, or 1 plus e to the 8 theta. Now, as a sidebar, we need to use another one of our derivative rules to take the derivative of e to the 8 theta. It is e to the 8 theta times the derivative of 8 theta. So the derivative of 8 theta is just 8. So this whole thing here that I just crossed out is actually 8 e to the 8 theta. Now let's bring up everything. And I'm going to erase this part since we're done with it now. Our dy d theta, we have 8 minus 8e to the 8 theta all over 1 plus e to the 8 theta power. Now, I do want to go a little bit further because some simplifying will actually happen. We can rewrite the 8 with the common denominator, 1 plus e to the 8 theta all over 1 plus e to the 8 theta. And let's bring over our second fraction. Now for this top part, we can distribute the 8. So that gives us 8 plus 8e to the 8 theta minus 8e to the 8 theta all over our common denominator, 1 plus e to the 8 theta. The reason why I went a little bit further with this problem is because at the end, our 8e to the 8 thetas cancel out. So our final dy dt is actually 8 over 1 plus e to the 8 theta. Let's look at another question in which you're trying to find the derivative of y with respect to an independent variable. Next question, we have given y equal to log base 10 of 9 theta. We need to find the derivative of y with respect to theta, or dy d theta. We're going to use our derivative rule here for log. So I'm just going to write the derivative rule up here and then we'll use it. In which u is our 9 theta and a is our base, 10. So the derivative of y with respect to theta, or dy d theta, is equal to 1 over u, or 1 over 9 theta, times natural log of a, or natural log of 10, times the derivative of u, or derivative of 9 theta. The derivative of 9 theta is the same as derivative of 9x. That's just plain old 9. Now we can cancel out that 9 with the 9 that's in our other part of our derivative. So our final answer, dy over d theta, is equal to 1 over theta times the natural log of 10. Make sure you have those rules handy that I shared with you earlier that will really help you when you're finding the derivative of y with respect to any independent variable like x, t, or in this example, the Greek letter theta. What you will also see in lesson 13 also involves taking derivative and using natural log properties, but you will have these directions. You'll have to use something called logarithmic differentiation. And what that means is in your problem, you have to, first of all, before you do anything, take the natural log or ln of both sides of your equation. So that's what logarithmic differentiation means. The very first step before you use any rules at all, you must take the natural log of both sides. Let's start with this example. We have y equal to x raised to the x plus 1 power. And we need to use logarithmic differentiation to find the derivative of y with respect to the given independent variable. For this problem, the given independent variable is x, so we're really trying to find dy over dx. The first step, take the natural log of both sides. Now, before we take the derivative of both sides, use your exponent law from natural logs to move the x plus 1 to the front. So that would give us x plus 1 times natural log of x. Now we're ready to take the first derivative. The natural log of y derivative is 1 over y. And remember, when you take the derivative of y with respect to your independent variable, you have to tack on a ratio, in this case, dy over dx. Now, to take the derivative of the other side, we must use the product rule for derivatives. So I'll label x plus 1 as our f, and natural log of x is our g. So let me write the product rule down and then we'll use it. The derivative of f, or derivative of x plus 1, times g, or natural log of x, plus f, x plus 1, times the derivative of g, or derivative of natural log x. Now, the derivative of x plus 1 is just 1. And over here, the derivative of natural log of x is just 1 over x. And technically, when you take the derivative of x, you still get 1, or still 1 over x. So let's bring down everything. We have natural log of x times 1 is just ln x, plus 1 over x plus 1, times x, Now, our goal is we're trying to find dy dx. But our dy dx is not by itself. Well, quite simply, to get dy dx by itself, just multiply both sides of your derivative by y. On the left side, the y's cancel, leaving us with dy dx. Now, we have a little problem. In our answer, we have two letters, x and y, but we need our derivative all in terms of x. All you need to do is replace y with what it originally was. Replace y with the x raised to the x plus 1 power. So this is our final answer. We have natural log of x plus 1 over x times x plus 1 times x raised to the x plus 1 power. And do not try to simplify. If my math lab marks this answer wrong, I will review and give you full credit if needed. Let's look at another example in which you must use logarithmic differentiation. So let me erase the whiteboard. And I'll put the second problem up here. All right, our second problem, we have y equal to the fifth root, and we have a fraction. T is in toy, all over t plus 1. And the directions say use logarithmic differentiation to find the derivative of y with respect to the given independent variable. Our independent variable here is t, so we're trying to find dy over dt. Before we take the derivative, let's rewrite the right side where it has an exponent. So the fraction can be rewritten as t over t plus 1 raised to the 1/5 power. So let me bring this over. Now, before we take the derivative of both sides, we must take the natural log of both sides. So we take the natural log of both sides. And we have natural log y equal to, on the right-hand side, use the exponent law for natural logs by moving the 1/5 to the front, giving us 1/5 natural log of t over t plus 1. Let's use another natural log property to break down our natural log even further. And we're doing this to make the derivative easy to find. We have a quotient, so we can separate this into subtraction. So 1/5 natural log of t minus natural log of t plus 1. Now we're ready to take the derivative of both sides. The derivative of natural log of y is 1 over y. And since we're taking the derivative of y with respect to t, we must include the ratio dy over dt. On the right-hand side, the derivative of natural log of t is just 1 over t. And the derivative of natural log of t plus 1 is 1 over your function t plus 1 times the derivative of your t plus 1. The derivative of t plus 1 is just 1. So essentially, our second fraction does not change. So let's bring up what we have. We have 1 over y dy dt equal to the entire right side and we don't have to multiply or get a common denominator. Now we're trying to solve for or find dy dt, but it's got that 1 over y attached to it. To get rid of that y, you just multiply both sides of your derivative by that y. Now the y's cancel each other out. Leaving us with dy dt equal to 1 over 5. Now, rewrite that y. Y was originally equal to our given fraction over here. So replace this y with that. The fifth root of t let me make that t smaller. T over t plus 1 times 1 over t minus 1 over t plus 1. And do not simplify. I will accept this answer totally broken down. Let's look at another example in which you have to use logarithmic differentiation to find your derivative. Given the fraction y equal to theta plus 7 all over theta times cosine theta, use logarithmic differentiation to find the derivative of y with respect to, in this case, theta is your independent variable. So we are trying to find dy over d theta. The first step, let me erase this. We already know what we're looking for. The first step is to take the natural log of both sides. Use the quotient rule for natural logs to rewrite the right side. Quotient rule means you break this down into subtraction. So we have natural log y equal to natural log theta plus 7 minus natural log theta times cosine theta. Now, because we have a product right here, we can expand that just a little bit further. The product rule for natural logs means you expand your natural log as addition. So we have natural log of y equal to natural log of theta plus 7 minus natural log theta plus natural log cosine theta. And let's go ahead and distribute that negative sign before we take the first derivative. That turns it into now negative natural log theta minus natural log cosine theta. Now, in order to have room to find the derivative, I'm going to erase the top part, kind of work our way back up. All right, now we are ready to take the first derivative of both sides. Derivative of natural log of y is 1 over y. And because we're taking the derivative of y with respect to theta, we must include the ratio dy over d theta. All right, now let's take the derivative of each natural log. The first one we have 1 over theta plus 7 times the derivative of theta plus 7 minus the natural log of theta is 1 over theta times the derivative of theta. By the way, later on today, after this video is done processing, I will share it in Blackboard on the announcements page. Minus the derivative of natural log of cosine is 1 over cosine of theta times the derivative of cosine theta. Now let's get these derivatives out of the way. The derivative of theta plus 7 is just 1. The derivative of theta in the middle, that's the same thing as taking the derivative of 1x. That's just 1 also. And the derivative of cosine theta is negative sine theta. So let's put everything together. 1 over y times dy d theta equal to 1 over theta plus 7 minus 1 over theta. And over here, we're going to simplify just a bit further. Negative divided by negative is a positive, and sine over cosine is tangent theta. So that's plus tangent theta at the end. Now we are trying to solve for dy d theta, but we have that 1 over y attached to it. Quite simply, as we've done with previous logarithmic differentiation problems, just multiply both sides by y. On the left-hand side, the y's will cancel out, leaving us with dy over d theta. And on the right-hand side, just replace y with its original fraction. So we'll bring down what's in parentheses. And replace the y with its original problem, theta plus 7 all over cosine theta. If you want to move this fraction to the front of the parentheses, then that's fine. Let's look at one more example in which you have to use logarithmic differentiation. Given the function y equal to x raised to the 7x plus 8 power, find the derivative, use logarithmic differentiation to find the derivative of y with respect to x. So we already know we're looking for dy over dx. Step 1, take the natural log of both sides. On the right-hand side, use the exponent law for natural logs to bring the 7x plus 8 to the front. Now we're ready to take the first derivative of both sides. The derivative of natural log of y is 1 over y. And because we're taking the derivative of y with respect to x, we include the ratio dy over dx. Now, to take the derivative of the right-hand side, we use the product rule. My 7x plus 8 is my f, and my natural log of x is my g. So over here, up top, let's write down the product rule. And fill in everything. The derivative of 7x plus 8 times the natural log of x plus 7x plus 8 times the derivative of natural log x The derivative of 7x plus 8 is simply 7. And the derivative of natural log of x is 1 over x. So let's bring everything down. We have 7 natural log x plus this last part here becomes a fraction now. 1 over x times 7x plus 8. Now, we are solving for or trying to get by itself the dy over dx. But we got that 1 over y attached to it. Quite simply, to get rid or to get dy dx by itself, multiply both sides of your derivative by y. On the left-hand side, the y's cancel, leaving us with dy dx. And bring down what's in parentheses. Now, we can't have a derivative. In this case, we can't have a derivative with 2 letters. So we got to replace that y with its original problem. So in place of y, we'll plug in the x raised to the 7x plus 8 power. And all of this right here is your final answer. A quick recap before we end today's lecture. This is what we went over today in lesson 13. How to take the derivative of an inverse function. How to find the value of the derivative of an inverse function. We went over the various derivative rules that you need to take derivatives of natural logs, exponential functions, and also logarithmic functions. We use various natural logarithmic algebraic properties to find derivatives with respect to various independent variables. And then finally, we use logarithmic differentiation, in which you have to take the natural log of both sides of your given equation in order to find a specific derivative. Again, I will post, once this video is done processing, I will share it with you guys in Blackboard. Just look under the announcements page.